Absorption and stimulated emission. In this section, we will study in some detail the processes of absorption and stimulated emission induced in a two-level system for a single atom interacting with a monochromatic electromagnetic wave. In particular, our aim is to calculate the rate of absorption W12 and stimulated emission W21 that we have seen in our previous lesson. We will follow the semi-classical approximation wherein, as already explained, the atom is quantized while the electromagnetic radiation is treated classically. It can be shown, in fact, that the quantum electrodynamics approach gives the same result as the semi-classical treatment when the number of photons in a given radiation made is much greater than unity. Since this applies to any system other than an exceedingly weak electromagnetic wave, we can dispense with the complication of the full quantum treatment. We will at first assume the two levels to be non-degenerate and treat the case of degenerate levels later in this chapter. Rates of absorption and stimulated emission. Let us first consider the case of absorption and assume that for time t is much greater than or is equals to 0. A monochromatic electromagnetic wave is incident on the atom so that the atomic wave function can be described as an equation the follow, where we will assume the initial conditions, the absolute value of A1 at 0 square is equal to 1 and A2 at 0 square is equal to 0. As a result of the interaction with the electromagnetic wave, the atom will acquire an interaction energy H and the treatment that follows this energy is considered to be due to the interaction of the electric dipole moment of the atom with the electric field E at r, t of the electromagnetic wave. The electric dipole interaction, where the origin of the r accordance is r coordinate is taken at the nucleus. The electric field at the nuclear position can then be written as E 0, t is equal to E naught sine omega t, or this electric field at 0, t is equal to E naught sine omega t, where omega is the angular frequency of the wave. We will also assume that the wavelength of the electromagnetic radiation is much greater than the atom's dimension, so that the phase shift of the electromagnetic wave over an atomic dimension is very small. Then, equation the following can be taken to give the value of the electric field for any location and the atom electric dipole approximation. We will also assume the frequency omega to be close to the resonant frequency omega naught of the transition. Classically, for a given position r of the electron within the atom would exhibit an electric dipole moment mu, which is equal to negative ER, where E is the magnitude of the electronic charge, the interaction energy H Hamiltonian resulting from the external electric field would then be noun.